Students, this problem is a classic limiting reagents problem, and what you really need to pay attention to in the problem are the coefficients in front of each of the chemicals that react. So there's a 2 in front of H2, an implied 1 in front of O2, and a 2 in front of H2O. What that means is, for every hydrogen molecule that reacts, you'll get a water molecule produced. For every oxygen molecule that reacts, you'll get 2 water molecules produced because of the coefficients. So in this equation, there's actually a lot of information just in the balanced equation. So for instance, 1 mole of oxygen is equivalent to 2 moles of water molecules produced. And just using coefficients from the equation, 2 moles of hydrogen that reacts is equal to 2 moles of water produced. You can reduce that ratio to 1 to 1. It's kind of like, let's say you run a bicycle factory, and in the bicycle factory you're making bicycles, so you consume 2 wheels for every 1 frame as you're producing bicycles. And let's say you're the director of the factory and you have to order supplies for every day, and you have to figure out, okay, how many wheels do I need to order and how many frames do I need to order in order to assemble the bicycles and have, if your goal is to have a matching number of those 2 supplies so that they are used up at exactly the same time, well, then you would order accordingly. In chemistry, rarely do the 2 reactants get used up at exactly the same time. Instead, there's usually 1 reactant that has some leftover. And that's what this problem is trying to get us to. So, for instance, in part A, they're telling us that we have 50 molecules of H2 and 25 molecules of O2. Now this just happens to be stoichiometric quantities, so that is, they are going to end up reacting away at exactly the same time. So let's say we're going to show work for this. Even if you can do this in your head, it's helpful to show work at first. Because of the coefficients in the equation, I can see that there's a coefficient 2 in front of H2. There's also a coefficient 2 in front of H2O. And so if I look at the units as they cross out, molecules of H2 crosses out and we'll be left with molecules of water. And since the lone product is the water, that's what we're interested in. So 50 times 2 over 2 will give you 50 molecules of water. The other consideration is how much oxygen you have. So 25 molecules of O2, and it's 1 molecule of O2 for every 2 molecules of H2O. The way I got that was by looking at the coefficients in the equation. The coefficient in front of oxygen is an implied 1, and so we put a 1 in the conversion factor. The coefficient in front of H2O is a 2, and so we put a 2 in the conversion factor. So 25 times 2 divided by 1 gives us 50 molecules of H2O. Notice that the units cross out. In this problem, it's one of those rare instances where the number of molecules of water produced by one reactant is exactly the same as the number of molecules of water produced by the other reactant if they both reacted away to completion. So for part A, the correct answer is none of the above. Neither of the reactants is limiting in that particular case. Let's look at part B. 100 molecules of H2 and 40 molecules of O2. Since there's coefficients of 2 in front of both H2 and H2O, if all of the hydrogen reacts away, then you'll have 100 molecules of H2O produced. If all of the oxygen reacts away, in this case 40 molecules of oxygen, and the ratio is 1 molecule of oxygen for every 2 molecules of H2O, we get 80 molecules of H2O. The limiting reagent is the one that produces fewer molecules of water. Since 80 is less than 100, that means that in this case oxygen is the limiting reagent. In part C, they give us 100 molecules of either reactant. 100 molecules of H2, and once again the ratio of H2 to water is 2 to 2, which is the same as a 1-to-1 ratio. So we'll get the same number of molecules of water produced as you had molecules of hydrogen that reacted. If all 100 molecules of O2 reacts, this time 100 times 2 divided by 1 gives you 200 molecules of water. It's kind of like these problems are twice as much work as a normal problem, because you have to solve it twice. You have to look for how much product is produced by reacting away the entire quantity of both of two reactants. And your goal is to pick the one that produces fewer product molecules. So in this case, since 100 is less than 200, we have to say hydrogen is the limiting reagent. It limits the amount of product that is produced. In part D, here they're giving us moles instead of molecules, but the exact same calculation is done. The ratio of molecules is the exact same as the ratio of moles of molecules. So they give us 0.5 moles of hydrogen, and just like before, 2 moles of hydrogen for every 2 moles of water. You'll end up with the same number of moles of molecules of water as you had moles of molecules of hydrogen that reacted. The other reactant was 0.75. This time you get 1.5 moles. You have to pick the one that is lower. So 0.5 is less than 1.5, therefore we have to say hydrogen is limiting in this case. Part E, they're giving us 0.8 moles of hydrogen And students, if you can take a shortcut and do some of this work in your head, go for it. It was 0.80. And they gave us 0.75 moles of O2. This work is actually also shown in Part D. So comparing 0.8 moles of water to 1.5 moles of water, you have to pick the one that is lower. And so again, hydrogen is limiting. In Part F, they're getting a little tricky on us. They give us 1.0 grams, not moles, but grams of hydrogen. And the other reactant, they give us 0.25 moles. So the one, in order to make a comparison, you've got to have units of moles, but they're like trying to be a little tricky here. 1.0 grams of H2, we need to convert into moles first. In that molecule H2, there are 2 hydrogen atoms, each of which has an atomic weight of 1. So the molar mass of the H2 molecule is 2 grams for every 1 mole. So we're just doing a molar mass conversion. We're getting number of moles of H2. And in this case, it works out to be 0.5 moles of H2. Once you've got that, then it's the same as parts D and E. So if it's 0.5 moles of H2, then go back to the equation and look at the molar ratio. 2 moles of H2 for every 2 moles of water. You get 0.5 moles of water produced. The other reactant they gave us in the problem in units of moles directly, so we did not need to use molar mass. And here we have one of those rare circumstances where the number of moles of water produced by one reactant is exactly the same as the number of moles produced by the other reactant. And so neither reactant is limiting. And so you would click the box that says none of the above on the WebAssign. Part G, here at least they're being consistent. They give us quantities of both of the reactants in grams. So in both cases you first convert from grams into moles, and then make the mole-to-mole conversion between the reactant molecule and water. 5 grams of hydrogen molecule, not hydrogen atom. Within the hydrogen molecule, H2, there are 2 atoms of hydrogen. So the molar mass is 2, not 1. That works out to be 2.5 moles. The other reactant they give us is 56 grams of O2. And within the oxygen molecule, there are 2 atoms of oxygen. Thus, the molar mass is 16 plus 16, or 32. And that works out to be 1.75 moles of O2. Now we've got the moles of both reactants, and we can just carry on like any of the previous problems. Using mole ratio, it's 2 moles of hydrogen for every 2 moles of water. So if you started with 2.5 moles of hydrogen, you'll end up with 2.5 moles of water. For the oxygen, it's 1.75, and it's a 2-to-1 ratio. 2 moles of water for every 1 mole of oxygen. And so you produce 3.5 moles of water. Our job is to pick the answer that is the lower of the two. So between 2.5 and 3.5, the correct answer is 2.5, which means in this part G, hydrogen is limiting. You would click that box.